Hello, I am Matt York, and this is exam 1, part 1 for Dr. Ko's class. We're going to be going over example 1.17, where we're dealing with this Stefan tube with acetone and methanol in the liquid phase down here, with air shooting across the top at a very high velocity. And this top has a screen, so the vapor phases of acetone and methanol are going to interact with the air as well. Oh yeah, one more thing to mention is the height positioning, Z equals 0 at the liquid vapor line, and it equals delta at the top of this Stefan tube. So what we are looking for is the order of magnitude. We're trying to define the order of magnitude through scaling of the molar flux of acetone and the molar flux of methanol. That is our goal here. And we are going to use differential equations with the Stefan-Maxwell diffusion coefficients and the equations they have with differential equations, with the relationships they have with differential equations to, in order to scale and scale these molar fluxes and find their order of magnitudes. So here we go. Starting off, we're going to start off with the rate of, the rate of acetone in regards to positioning in the tube. So the amount of acetone in regards to the positioning of the tube. This is equal to, by definition in our book, the equation, the mole fraction of acetone multiplied by the mole flux of methanol subtracted by the molar fraction of methanol multiplied by the molar flux of acetone. This is all divided by the total concentration of this mixture multiplied by the Stefan-Maxwell diffusion coefficient of acetone and methanol. This is added to the molar fraction of acetone multiplied by the molar flux of air, subtracted by the molar fraction of air multiplied by the molar fraction or molar flux of acetone. This is divided again by the concentration of this mixture this time and multiplied by the Stefan-Maxwell diffusion coefficient for acetone and air, which we are also given in this problem. Sorry I didn't go over this, but we are given the temperature, the delta, which is the height at the top of the Stefan tube, the molar fraction of acetone, the molar fraction of methanol, and the molar fraction of air. We're also given the Stefan-Maxwell diffusion coefficient of acetone and methanol, acetone and air, and methanol and air. So going off of that, we are actually going to also define the rate of methanol in regards to the height of in this vapor phase as well, which is Z. So that is very similar to the rate of acetone in it, but now it's just with what methanol is reacting in. So now we have the molar fraction of methanol multiplied by the molar flux of acetone subtracted by the molar fraction of acetone multiplied by the molar flux of methanol. Sorry, I'm getting confused with my with which is which. But anyway, yeah, it's molar fraction of methanol multiplied by the molar flux of acetone subtracted by the molar fraction of acetone multiplied by the molar flux of methanol. And then this is over the total concentration of this mixture multiplied by the Stefan-Maxwell diffusion coefficient of acetone and methanol. And this again is subtracted by the other interaction with methanol, which would be with air. And methanol is, we're again starting with the methanol mole fraction multiplied by the molar flux of air, subtracted by the molar fraction of air, multiplied by the molar flux of acetone. Again, over the concentration of this mixture, over the Stefan-Maxwell diffusion coefficient of methanol and air. Okay, so after writing those down, we are actually going to scale this using a variable called eta, which is defined in the book as z, which is our position, the height positioning in this tube, over delta. Well, what that does for us is it scales this height in this vapor phase to between 0 and 1, because when we put z equals 0 into this equation, we get 0. And then when we put z equals delta in this equation, well, z and delta equal, it would equal 1. So now we know that eta is scaled between 0 and 1 in this height of this vapor phase. Well, that is going to come in handy in a second. So first off, let's put all of our variables in terms of eta now instead of z, because now we have it scaled from 0 to 1. Well, if we do that, we have the derivative of molar composition of acetone in regards to eta. Let's see, can you see? Yeah, perfect. In regards to eta, if we want that to be equal to our rate of acetone in regards to z, then we need to multiply this by the derivative of eta in regards to z. That's just a manipulation of equations, just because these two would cancel out, and you'd get, again, your rate of acetone in regard to the positioning in the tube again. So now that we have this, we have to see what we have. So we know this. This is known because it's up here. We just defined it. And we can find the derivative of eta in respect to z because we have eta. So let's just do that. Derivative of eta in respect to z equals, well, we have a constant 1 over delta multiplied by your z, which if we just take the derivative in respect to z, that's just 1, and we get 1 over delta. So this is our derivative. Now this is known, and we can put this in for that, leaving us with one variable, the rate of acetone in respect to eta. But we are going to write this out and see what that actually will give us. So with one unknown. So now we're going to write this out. We have the derivative of molar fraction of acetone over, or in respect to eta, times 1 over delta, because we just defined that, is equal to what we wrote up here. I'm not going to define this again because it takes a while, but I'll just write it out. We already defined this. All right, and oh, I have not mentioned this yet. So we have the molar flux of acetone and the molar flux of methanol, and we're trying to find the order of magnitude of these, and we're trying to scale them to find the order of magnitude of these. Well, we also have in this equation the molar flux of air, which doesn't really make sense because there's no air diffusing through this tube. We have vapor phase coming out and interacting with this air, and that's why we have these mixtures, but we don't have any air diffusing in this tube. So this would actually just be 0. We can simplify those equations and have them be 0, which would take away this term, and we don't even have to write that out. And we didn't simplify this either, so we have y3. Yes, that is given to us, but to make our lives easier and define it, as we can define it in terms of y1 and y2, because mole fraction, what's mole fraction? Mole fraction is simply all of the components of a system, the mole fraction of each component of the system, summed together is 1. So we can just play with that. Y3 would equal 1 minus y1 plus, minus y2 would equal y3, because we just subtract both those over. Okay, so what we're going to do now is we're going to take 1 Oh gosh, you know what? I'm just gonna subtract it here. Oh wait, no, it's not subtracted here. Is it added? Okay. We are going to take 1 minus the mole fraction of acetone, subtracted by the mole fraction of methanol, and substitute that in for Y3, and we can't forget this negative sign. So I guess I could have left that negative, but whatever. We can't forget this negative sign for that's in front up here, if you can see that. All right. Well, knowing that, that's still over the concentration multiplied by the diffusion, Stefan-Maxwell diffusion coefficient of acetone and air. Okay, sorry, I'm losing myself for a second. Let's get back. This is what we defined earlier, and we just sub some variables in. That's all we do. Okay, so knowing this, we can just multiply each side by delta, because let's just get rid of this delta over here. That way we can just simplify it to the rate of acetone in this system in regards to eta, the height in the vapor phase. So, boom, there goes your delta, and we'll add a delta over here on each side. Add a delta. All right, well, let's see. What do we know about each of these variables? Now, let's see if we can define the order of magnitude for each of these variables, because we're trying to define it for N1 and N2, which is Mohr flux of acetone and Mohr flux of methanol. Well, we know that, let's start on this side actually. We know that Mohr fractions have a, sorry, let me say this again. I'm confusing myself. We know that Mohr fractions, okay, sorry, it almost paused there. Okay, all right, I'm gonna say this the third time. We know that Mohr fractions are scaled by 1, as we defined here earlier, because all the components summed up together equal 1. So we know that the order of magnitude for mole fractions would be 1. Well, this is in respects to eta, but what did we already define earlier? We defined that eta is in an order of magnitude from 0 to 1. So this side can all be an order of magnitude of 1. We know that. We can define it as 1. Make sense? This, if both the numerator and the denominator are both scaled in order of magnitude of 1, then we can scale this whole side as 1. Well, knowing that, we know that this whole chunk and this whole chunk have to be defined in order of magnitude of also N1. Well, the great thing is, actually, let's slow down for a second. What do we know already in here? What do we know the order of magnitude of? Well, we know delta is 1. We know the Mohr fraction of any of these components is also 1. We know the Mohr fraction component 1. And we don't know the Mohr flux of either of these components. We don't know the scale. That's what we're trying to find how to scale. But the good thing is, we know that this as a whole has to equal 1. And this numerator over this denominator, that means the numerator over the denominator must also be an order of magnitude of 1, equal to it. So if we're trying to find the order of magnitude of the Mohr flux of methanol and the Mohr flux of acetone, then we know that that order of magnitude has to equal the order of magnitude of the denominator. Beautiful, right? Well, what is the concentration? We don't have the concentration here, but we do have the pressure, we have the temperature, and we know a relationship between concentration, pressure, and temperature, which is beautiful. So multiplying this by your Stefan-Maxwell diffusion coefficient, we should be able to scale this. So first, pressure. What do we have here? We have 99.4 kilopascals. Well, we want to put it in terms of pascals. So if it's kilo, it's times 10 to the third, which means this would be 10 to the fifth on top. And on the bottom, we have R, which is 8.314, which we can really just call 10 or magnitude 10. And temperature, which is 325.5, which we can just really call 100. Well, if we're multiplying 10 by 100, we know that that's 1,000, right? And we also know that this diffusion coefficient, these are, oh gosh, I didn't write these down. I forgot that I'm going to. All right, so my camera just cut out, but I found out that it is 8.48 millimeters squared per second, which is, after doing calculations, I figured out that it is 8.48 meters squared per second times 10 to the fifth, which equals, so we have 10, 100, 10 to the fifth, which equals the pressure when we put kilopascals to pascals. So the pressure and the diffusion, Stefan Maxwell diffusion constant coefficient would cancel out, giving us 10 times 100 on the denominator, which would be 1 over 1,000, which equals 10 to the negative third, which is what we found the order of magnitude to be for the Mohr flux of acetone and the Mohr flux of methanol. Thank you very much. Take care. Have a great day.